Oh, what do the Higgs boson, the Planck mass, and Hbar have in common? Sounds like the beginning of a bar joke. Is there more? Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one rule ad. I don't think it rules them all. And it might be just hyper-rurial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rurial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
So, now that somebody may have actually clicked this or the algorithm dragged you here for some reason or another, hey guys, what's going on? Memes here. And yes, we're going to be talking about what some have claimed is the God particle and everything. Why? Well, according to the Wikipedia entry, the word God appears 44 times. I'm sure that's just a coincidence. But that aside, again, Wikipedia, take it for what it's worth. It's not a bad first level approx. I see a lot of smart people that have published a lot of things using it, at least as a cursory thing to find source and stuff. But what is this? Real quickly, the Higgs boson, sometimes called the Higgs particle, rest in peace, Peter Higgs, is an elementary particle in the standard model of particle physics produced by the quantum excitation of the Higgs field, one of the fields in particle physics theory. And the standard model, the Higgs particle, is a massive scalar boson with zero spin, even positive parity, and no electric charge and no color charge that couples to interacts with mass. It is also very unstable, decaying into other particles almost immediately upon generation. Okay, the whole thing is, and you see this picture here. So, and again, credit to CERN because it's the CMS experiment at LHC. Okay, so basically the whole thing, as far as I understand, again, I'm not a professionally trained physicist. Take it for what it's worth. But essentially, you see these lines here. Those are essentially the photons that they detected that essentially they were able to derive the Higgs boson mass energy equivalence. Because when we're measuring things, basically we can use electron volts to model almost anything. That's like one of the crazy things when you start looking at this. It's like, all right, mass, we have it in electron volts. Length, we have it in electron. You're like, what? Because human beings are really clever. And we've literally got millennia or probably millions of human years dedicated to figuring these things out. So thank you, because it also helped give birth to things like Wolfram Alpha. I'm sharing tab, not the thing. Okay. Bad host. But yes, welcome one and all. Oh, hello, Rick. Good to see you, my friend. Yes, we're gonna get into the fun stuff here. What am I doing? No, that's the wrong button. Okay. Yes, I can really, my computational ability to do multiple things is limited. Here we go. Share the actual one. Okay. So over here we have our friends. Okay. So basically what I noticed is I was looking at this, and at first let's do this. I'll do a new one because we're gonna have some fun here. So I'm like, all right, what's this? Because I hear all about particle physics and stuff like that, and basically we have electromagnetism, we have the effects of gravitation, and then basically there are only so many. I hear many folks say, well, a neutron has a jiggle in the neutron field. A proton has a vibration in the proton field. I'm always looking for computational reducibility, pardon the Freudian slip there, to help make things easier. So what happens? If we get the Higgs particle, boom, it comes up. It gives you this information. I'm like, okay, gives us a symbol. It gives us the possible mass. And this is basically combining a couple of different experiments. I think we had the 2022 and 2023 runs of the LHC there. Okay, so it's about 133 proton masses. But for those that pay attention, there's another tab here. You click more. Okay, so it gives you basically, I looked at this. I found some interesting things, and I'm sure it's very trivial and everything. You looked at this, because that's right around... I think the classical radius of the proton, or one of those things. It was pretty close. It's right about 2 pi, but it wasn't quite 2 pi. Maybe it is 2 pi if it's slightly under 125 GeV. Again, we're going to have to follow the information. That's what science is. At least I've been told that. Okay, so you got all these things. Okay, so ultimately, I looked at this and I started relating some different things. I'm like, all right, let me look at this 28 GeV. What is this? I'm like, okay, so it gives me the mass equivalent. Okay, let's just do straight GeV because we divide it by giga-electron volts, divide by c squared to get the rest energy mass. E equals mc squared, yada, yada. Okay, cool. So I looked at these things and I'm just like, okay, the Higgs field, if it happens to have this excitation energy approximately, and again, maybe there's a spread there, possibly, I don't know. How could I relate it to something? I relate it to like the proton mass. I relate it to the electron mass. I'm looking for things. I can grasp for some straws. But ultimately, I'm like, spent a lot of time kind of, or at least for me, just around doing the internet. I spent probably more time I should have looking at things like the fine structure constant. And when you realize there's certain combinations of things you could do, because what is it? The fine structure constant as we know it. Alpha, the official definition, is elementary charge squared. So basically the charge of the electron of the proton. And since you square it, doesn't matter the symbol. That's interesting. And you got all that divided by 4 pi times the speed of light times the electric constant times Hbar. Whoa, so we got a lot of stuff, and this thing pops in all the time in physics, all over the place, relating different ratios and stuff, yada, yada. Okay. So the interesting thing is that number right there, you can acquire by doing this. Elementary charge squared, but the denominator is actually equal to the Planck charge squared. Again, that's interesting. Trivial. Basically, there's an error on like Wolfram Alpha right now, so it's a little mucky with the update on units, because if I just do this, I think it will give me an error. Maybe it gave me an error. Okay. But ultimately, that would be equivalent because it's squaring everything in there. It's just redundant notation. Okay. So what I ended up doing was, I'm like, all right, we get this under 25.18 giga electron volts. I'm like, okay, what can I relate it to? Initially, I did the Planck energy because I'm like, well, we set these things to 1. If we set that to 1, if we set the Planck energy to 1, if we're assuming some form of oneness. Okay. I did that. Ultimately, it ends up being easier to just do it with mass because there's a mass energy equivalence. Again, thank you, all the folks in the past. I would just say Einstein, but there were a lot of other folks that had other derivations too. But, okay, so what we find here is if basically I played around. So let's take Hbar out of the equation, literally. Okay. So we take the Higgs boson mass, and we divide it by the Planck mass. Okay. We'll start off small. Just see if there's any relationship. Because it doesn't like doing it that way, does it? Okay. I'm sorry. It's giving me the unit errors here. Perhaps it's just the user error. Okay, so let's do that. I think it likes doing the big one. Okay, so it gives me that. It's because it probably would have returned a really, really small result. Okay, so I get this. So I played around with the speed of light because that's approximately close to the speed of light. I could try to say things, didn't really have much confidence, nor it required tweaking and stuff. So maybe there's something there. But when we square the number, let's see if it will allow me to do this. It should, since it's a bigger number. Okay, it doesn't like that form, so let's just go back. Boom. Okay. So let's just try this. Will it return the number, or does it need the... Okay. So, oh God, this is very embarrassing. Okay, we'll just go to this. Ultimately, when you divide the Higgs boson mass by the Planck mass, and you square it, you basically get the magnitude of the difference between Hbar and 1 joule second. So, because joule seconds are how we measure units of action or angular momentum, because that's how we do Planck's constant, Planck's reduced constant, yada, yada. So all I really did was just assume some form of, all right, there's something interesting going on here. I was using the exact same construction that you can use for the fine structure constant. But ultimately, it comes down to boom. So basically, you take h bar, you divide it by the square of the dimensionless relationship, because when you divide a unit of mass by another unit of mass, they're the same exponents, it cancels out. And you happen to get 1 joule second, or 10 to the 7 erg seconds, which I think the erg is a very, very underutilized unit. I'm just saying, I think these things may help us. And again, perhaps this is just a trivial, again, I'm sure it's just a trivial thing due to the way we have our mathematics and units defined. I just happen to think that was really cool, because you can also express it the other way too. So basically, Planck mass divide by the Higgs boson mass, and then you just multiply it by it. So again, just basic multiplication and division. We get the same thing. So again, we're basically following this the same thing. We'll just take a thing, take another thing, throw on some brackets, square them both, and see what we get. So 10 to the 7, Rick. Yes, 10 to the 7. This is the thing. When you look at these things in ergs and everything, I really feel it's a very underutilized unit. Yeah. 10 to the 7 erg seconds in this case. It's very interesting, because you see this with Ampere's constant. You see this with other things. It appears that maybe something interesting is going on around those magnitudes there. Hey, Keishel, good to see you, my friend. But it is very interesting. And then I still need to do a video at some point, actually, like craft something somewhat decent, because apparently they found some form of superluminescence, maybe not directly related to microtubules, but like the different tubular structures and everything, which, what is it? I'll do it real quick. Microtubule. So, all right, just again, first level approximation, Wikipedia. What's the deal? Is there a magnitude or scale? Oh, look. As wide as 23 to 27 nanometers. Okay, so let's shortcut that. Try 25, smack down in the middle. What's 25 nanometers? 25 nanometers is, oh, look, it's in the realm of 10 to the negative 8, so within a magnitude there. What does that mean? I have no idea. It's just things tend to kind of get quantumish, or at least those are effects that we really start seeing around 10 to the negative 7, 10 to the negative 8, and coincidentally, if you take the inversion, once you start approaching the speed of light relative to observers like us, things also start to get a little wonky. Is something interesting going on there? I'm very biased. My opinion, I think there is. But hey, I'm just a dude on the internet, and I just happen to think that it was pretty cool that you take some very basic things that, due to the sum total contribution of humanity, I can type these things on my computer and get something that gives us a form of a oneness there. Does this mean anything? I don't know. Maybe somebody out there will figure out. Maybe somebody's already figured it out. I guess we're going to have to wait and see, but I'm pretty sure there's enough smart folks out there that we'll be able to get this. Human beings are pretty smart, so that's all I got for right now. Peace out, everybody. Take care of yourselves. Links, of course, are in the doobly-doo, and hey, let's do a great year coming up for science. Peace out, everybody.